Okay, further maths. So this is Core Pure, Year 12 January Assessment, Year 2022. Just going through the solutions here. All right, question number 1. So we've got two matrices, P and Q. We're asked to describe the single transformations P and Q represented by these matrices for 4 marks. So part A, all right, so consider what happens to the points 1, 0 and 0, 1. So 1, 0 has moved to 0, 1 and 0, 1 has moved to minus 1, 0, so it's gone down to there. So therefore this is a rotation of 90 degrees anti-clockwise about O. Okay, so you get 1 mark for saying it's a rotation and 1 mark for saying it's 90 degrees anti-clockwise about O. Oh, that's P. Matrix Q, the 1, 0 has stayed as 1, 0 and the 0, 3 has stretched up. So therefore this is a stretch scale factor 3 in the Y direction. All the Y coordinates have been multiplied by 3. Okay, again, 1 mark for saying it's a stretch, and 1 mark Y scale factor of 3 in the Y direction. All right, part B. The transformation P followed by the transformation Q is the transformation R. This is represented by the matrix R. Determine R. So P followed by Q means the matrix Q multiplied by P. So it reverses the order. So R is going to be equal to Q times P. Okay, that means P first, then Q. So that's going to be 1, 0, 0, 3 times P, which is 0, 1, minus 1, 0. And that comes out to be 0, 3, minus 1, 0. Evaluate the determinant of R. That's going to be 0 times 0 minus 3 times minus 1. So 0 times 0 minus 3 times minus 1, which is 3. You can just state 3, it's only 1 mark. D, explain how the value obtained in C relates to the transformation R. So you need to say that the area scale factor is 3. So you refer to the area scale factor. And then finally, as a little separate 2 marker, write down the matrix which represents a skew parallel to the x-axis such that the point 0, 1 maps to the point 1, 1. Okay, well 0, 1 maps to the point 1, 1. That tells you that the second column is 1, 1. And it's a skew parallel to the x-axis, so therefore any points on the x-axis remain on the x-axis where they are. So it is 1, 0. Okay. Question number 2. Use standard series formulae to find this sum, factorising your answer as far as possible. So what I'm going to do is I'm going to say that this sum is equal to r cubed plus the sum of r. I mean, this is bad maths notation, but in your working, it's fine to use. Sum of r cubed is given in the formula book, so that is a quarter n squared n plus 1 squared. And the sum of r, you need to know that one, but it's the square root of that, coincidentally. It's a half n times n plus 1. So add those together. We need to factorise it as far as possible. So the smallest fraction which is going to go is a quarter. There's an n in both terms, and there's an n plus 1 in both terms. So n and n plus 1 can come out. What's left on this first term is the other n and the other n plus 1. And what's left here is, well, the n and the n plus 1 have both come out, but a quarter's come out, therefore I need to plus 2 to that. So that the 2 times a quarter gives me the half. Simplifying that a little bit, I'll get a quarter n plus 1, n squared plus n plus 2. And a quick check of b squared minus 4ac, which comes out as a negative number, tells you that that will not factorise. Therefore, that is as simple as it goes. Okay, we don't use complex numbers for any other questions other than complex number questions. Okay, so for a standard series question, we don't use complex numbers. So therefore, that is factorised as far as it will go. That's the answer. Question 3. All right, so we've got M and N as two 3 by 3 matrices. Determine in its simplest form, in terms of K, the matrix M times N. So part A, M times N. We've got K's kicking around. It makes sense to just look at the coefficients of K's and the constants separately. So this top row times this left column, for example, we're going to only have 2K. So therefore that's a 2K. And the constant is going to be minus 14 plus 2 minus 12. So that comes out as a minus 24. And we can follow it all through the same process. We'll get 0, 0. Here we'll get a K squared minus 7K plus 10, because we end up with a K times a K. We'll end up with 6K minus 44, and then a 50 minus 10K. 4K plus minus 20, 0, and minus 14. For 2 marks, it is quite a lot of work, but that's the answer. Part BI, given that K is 5, write down the matrix MN. You just plug in 5 into what you just got here, okay? And it comes out as minus 14, 0, 0, 0, minus 14, 0, 0, 0, minus 14. And then it says, hence, write down m to the minus 1. Well, because m times n is a multiple of the identity matrix, then m to the minus 1 is that multiple as a divisor times n. Okay, because that's just a scalar factor that can come out. And you don't have to write down the whole matrix, you can write down minus 1 over 14 to the n, times n. That is fine. Part C, use a matrix method to solve these equations. What you should notice is that the coefficients of these 3 equations matches the coefficients of this up here, as well as the fact that K is 5. Okay, so K is 5. So we have the inverse. So part C, solving a matrix equation, x, y, z is going to be inverse m times the vector, which in this case is 2, 3, minus 1. Okay, 2, 3, minus 1. So we can have minus a 14th times n when k is 5, which is minus 2, 6, minus 10, 2, minus 20, 24, minus 3, 2, minus 1, times that vector of 2, 3, minus 1. Multiply all that out, we will arrive at the fact that x equals minus 12 sevenths, y equals 40 sevenths, and z equals minus 1 14th. You cannot just state the answer to that and expect full credit, because the question has said explicitly to use a matrix method. So if you don't write down some kind of matrix equation in your attempt to solve it, you will not get full credit. Okay, I know your calculator can solve those, and so do the examiners. So don't do it. You can use it to check, of course. Part D, interpret your answer to part C geometrically. Well, minus 12 sevenths, 40 sevenths, and minus 1 14th is the only point in 3D space where these 3 planes intersect. Right, question 4. Figure 1 shows an Argan diagram. The set P of points that lie within the shaded region, including its boundaries, is defined by this. We told A and B and C and D are integers. Write down the values of A, B, C, and D. Okay, right, so we're told that Z is complex, such that the modulus of something lies between A and D. Well, the modulus is all to do with the radii, or radius of a circle. So this is going to be the smallest radius, and this is going to be the biggest radius. So if we look at here, we can see that the radius of the smaller circle is 1, and the radius of the bigger circle is 2. So that tells us then that A is 1 and B is 2. So A equals 1. B equals 2. What this B and D equals 2. Apologies. What this B and C do is it's going to translate. Okay, if it was just a Z in that mod bracket, then the center would be the number 0. However, it's not, it's been moved to minus 2 plus I, so therefore this needs to compensate for that, and it is the negative of that centre. So because I've moved minus 2 in the real direction, then I must have moved 2 here, so therefore B is 2. And because it's positive 1 in the I direction, in the imaginary direction, then that means that must be minus 1. So that when I have Z plus 2 minus I in the mod bracket, when Z equals minus 2 plus I, then that mod is 0, which is the centre of the circle. Okay. You get 1 mark for getting 2 of those correct, a 2nd mark for getting a 3rd one correct, and the 3rd mark for getting all 4 correct. Okay, part B, the set Q is defined as this thing. It's the same left-hand side. Okay, so it is this region, and we're given this. So we're told the modulus of Z minus I is less than the modulus of Z minus 3I. So you need to know this is a perpendicular bisector line, and it's a perpendicular bisector of these 2 points. Okay, so I and 3I. So therefore the perpendicular bisector then is here. Okay, that's the perpendicular bisector, and we want the side that includes the I side, so we don't want that top. So the region that we're trying to find the area of is kind of this portion of the, I'm sorry, can't see it, this portion of the annulus. Okay, so what I'm going to do then is I'm going to first of all treat this as a disc, just a big disc with a radius of 2, and I'm going to take off this sector and add on this triangle again, and what that's going to do, it's going to give me the area of this this portion. So it's the circle with the cap taken off the top, and then finally I will remove the area of the circle here, and that will leave me with the shaded region, which is what I'm trying to find. This is 7 marks, so it is quite a lot of work. Okay, so I need 4 areas. I need the area of the big circle, I need the area of the small circle, I need the area of the sector, and I need the area of the triangle. Okay, let's start with the easy ones. So area of the big circle, well, that's going to be pi r squared. R is 2, so that's 4 pi. I want the area of the small circle. Again, pi r squared, this time r is 1, so that's just pi. I want the area of the sector. A little bit trickier. I need some angles going on here, so I'm just going to pull out this triangle there. This length here is 2 because that's the radius of the big circle, and that length there is 1 because that's the radius of the small circle. By Pythagoras then that's root 3, and it's fairly easy to arrive at the fact that this then must be pi on 3 or 60 degrees. Okay, so the angle there is 60 degrees. By symmetry then, this is also 60 degrees, so we end up with 120 degrees. So it's a third of that circle, is that sector there. So I know the big circle is 4 pi, so a third of that then is 4 pi on 3. So the area of the sector is 4 pi on 3. And I also need the area of the triangle, okay, because I want to first of all work out the area of this circle with the cap taken off. So I need the area of the triangle to add it back on. And the area of the triangle is a half AB sine C. So C is 120 degrees. So the area of the triangle is going to be a half times A times B, they're both 2, times sine of the angle in between them, which is 120 degrees. And if you plug all that through, that comes out as being root 3. Okay, so I've now got all my pieces that I need. So the area of Q, which is what I'm trying to find, is equal to the big circle, subtract the sector, add on the triangle, and then I need to take off that inner circle. And if you simplify all that down, I'll get 5 pi on 3 plus root 3. And that's the answer. Okay, quite a lot of work there, and lots of thinking about how you're going to add and subtract all these areas, but that's how it's done. Question 5. Okay, show that M is non-singular. Okay, so the determinant of M is minus 28 at plus 10, which is minus 18. That is not 0, therefore non-singular. Okay, by definition, the determinant of a matrix, the determinant of a singular matrix is 0. So the determinant of a matrix is not 0, it's not singular. Part B. Transformation T of the plane is represented by the matrix M. The triangle R is transformed to the triangle S by the transformation T. Given that the area of S is 63 square units, find the area of R. Okay, so you need to use the idea that the new area is equal to the old area multiplied by the modulus of the determinant of the matrix. Okay. So we know that the new area is 63. We don't know the old area. We know the determinant of the matrix is minus 18. So the modulus of minus 18 is just 18. So the area then is 63 divided by 18, which is 3.5. That's the answer. Part C, find the matrix that would transform the triangle S to the triangle R. So M takes you from R to S, therefore inverse M will take you from S to R. So we need to inverse M. So you can just state it, M to the minus 1 is 1 over the determinant, so minus 1 over 18. Swap the lead diagonals, so the minus 7 and the 4 have swapped places, and change the sign of the other two. So the minus 5 becomes positive 5, and the 2 becomes negative 2. And that's it. And you can just leave it like that. That's fine. Okay, 3 marks for that. Question 6. For this question, you must show detailed reasoning. Okay, you can't just number it in your calculator. Expect full credit. Okay, we've got 3 complex numbers. We've got Z1, Z2, and Z3. They're defined here. So we've got minus 2, minus 1 plus 2i, and 1 plus I. And we're asked to calculate a 4th complex number, which is given as this relationship here. And we must leave our answer as a plus bi, where a and b are real constants to be found. Okay, so Z2, or Z4 is equal to Z2, which is minus 1 plus 2i. Minus Z1, so that's minus minus 2, divided by Z3, which is 1 plus I, minus Z1, which is minus minus 2 again. So that gives me 1 plus 2i divided by 3 plus I. Okay. Now that's the correct division, however, that's not in the form that it wants. It wants it in a plus bi. So I need to times it by its conjugate to make the bottom real. Okay, it's the same process that we would use to rationalise the denominator of a number, an integer plus a surd. So the numerator is going to become, well, the real part is going to be 3 minus 2i squared, so that's 5. The imaginary part is going to be 6 minus 1, which is 5. Denominator, the 3i and the minus 3i, they're going to cancel, which is why we're doing what we're doing. The real part is going to be 3 times 3, which is 9, minus I squared, which is minus 1. So 9 minus minus 1 is 10. So that comes out to be a half plus a half I. And that's the answer. Part B. Find the modulus of Z4 and show that the argument of Z4 is pi on 4. Okay, well, we can see the argument of Z4 is pi on 4 because the real and imaginary parts are the same. And the argument is defined as arctan of the imaginary part of the real part. You may need to add or subtract pi to that. So it's a half divided by a half, which is arctan of 1, which is pi on 4. We need to find the modulus of Z4. So modulus of Z4 is equal to the square root of a half squared plus a half squared. So that comes out as root 2 on 2. So we've we've got the modulus and arctan. So 2 marks for showing that's pi on 4, and 2 marks for correctly calculating the modulus. And finally, part C, hence write the complex number Z4 in modulus argument form. Well, that is the modulus of the complex number times by the cosine of the argument, which is pi on 4, plus I times the sine of the argument. That is modulus argument form. Okay, very useful in second year. We take this and go a lot further, so make sure you are happy with modulus argument form. Okay, that's question 6. Question 7. Explain why a cubic with real coefficients must have at least one real root. Okay, so for 1 mark, you can argue this one of 2 different ways. You can either say a cubic graph must cross the x-axis because it starts low and ends high. Okay, so all cubic graphs will start down there and end up there, or they'll start up there and end down there. It has to cross the x-axis to cross that threshold. So you can argue it graphically. A better way to explain it is a cubic equation with real coefficients will have complex roots appearing in complex conjugate pairs. But a cubic has 3 roots. Therefore, at least one is real. Or something to that effect. Okay, given that D is real, okay, so we've got a cubic equation here. D is real, so we've got a cubic equation with real coefficients. And a third minus I is a root of the equation fz equals 0. For 1 mark, write down the other complex root. Well, as I just said, any complex roots must appear in complex conjugate pairs, so therefore we must have a third plus I is also being a root of that equation. C, find the real root of the equation and hence find the value of D. Okay, well, we can use the fact that the sum of the roots is equal to that divided by that. So the sum of the roots, we've got a third plus I is one root, plus a third minus I, plus the third root. That is going to be equal to minus 39 on 9. Okay, that's using that kind of sum of the roots idea. Some of the couplets would be that over that, and some of the product would be minus that over that. So it's using those formulae, and that gives us then just a linear equation in D, which we can go ahead and solve. And we arrive at the fact that D is 50. And we're also asked to find the value of the, oh no, that's the real root, apologies, I'm jumping ahead of myself. Alpha, the real root is minus 5, and now we can use the fact that the product of the roots is D, so we end up with a third plus I times a third minus I times minus 5 equals minus D on 9, and that tells us that D is 50. Apologies. Okay, so those are the answers there using those formulas. That's the best way to do it. Part D, show the roots f of z equals 0 on a single Argans diagram. So we've got minus 5, that's real, and then we've got a third plus I and a third minus I. And that's the real axis, that's the imaginary axis. There we go. Okay, question 8. All right, part A, find the value of k for which this matrix does not have an inverse. Assuming that k does not take this value, find the inverse of m in terms of k. So rather than just calculating the determinant of this matrix in terms of k, I would actually look to find the inverse of it altogether, because I need to do that anyway. So I'm going to crack out my usual method for finding the inverse of a 3 by 3. I'm going to say element cofactor and det, and make myself a little table. And I can't get everything in shot here, so I'm gonna do that. I think we can just see it. Okay, I'm going to go in the rows. So 1 minus 1k is the first row, 5, 4, 6 is the second row, and then 3, 2, 4 then is the third row. A cofactor then is defined as the determinant of the minor multiplied by the sign. So the sign of this one, this one, this one, and this one is negative, so don't forget to times that determinant by -1. Okay. So this element here, number 1, is this element here. So delete the column, delete the row. Determinant of that is 16 minus 12 is 4, times by +1. This one here, 5 times 4 is 20, minus 3 times 6, that's +2. However, it's in a negative position, so therefore that's -2. And then the k, we've got 10 minus 12 is -2, and that's in a positive position, so -2. The determinant then of this section is 4 plus 2, because times them and adding them, minus 2k. So that is 6 minus 2k. All right, do the same thing with the 5. It's in a negative position. So the determinant, minus 4 minus 2k, that needs times by -1. So I get 4 plus 2k. The 4 is in a positive position, so I get 4 minus 3k. And then the 6 here, I've got 2 minus -3 is 5. That's in a negative position, so -5. And again, element times cofactor, and do a sum product of those. So the number we've got, 5 times 4 is 20, plus 4 times 4 is 16, so that's 36. And then 6 times -5 is -30, so that's +6. And then the coefficient of k, I've got 10k minus 12k is -2k. That's reassuring that they're both the same. And then finally the bottom row, the 3, we've got -6 minus 4k, that's a positive position, so it stays at -6 minus 4k. The 2 there, we've got 6 minus 5k, but that's a negative position, so 5k minus 6. And then the 4 is 4 minus -5 is 9, and that's a positive position, so that's fine. Again, looking at constant, we've got -18, minus 12 is -30, -30 plus 36 is 6, and then -12k plus 10k is -2k. The fact that all 3 of those are the same is very reassuring indeed. Now that we've filled out that table, we can state the inverse as being 1 over the determinant, which is 6 minus 2k, multiplied by the, I can't remember the word, transpose, thank you, the transpose of the original matrix. So these were the rows in the original matrix, so therefore these are columns. Okay, if you chose the columns here, then these would be the rows. Okay, so we're now going down the columns. So that's 4 minus 2 minus 2, 4 plus 2k, 4 minus 3k, and -5. Then we've got -6 minus 4k, 5k minus 6, and 9. And that is the inverse. And this is true for k not equal to 3. Okay, and that is the answer to this part of the question. Find the value of k for which this does not have an inverse. All right, the value is 3. If k is 3, the inverse wouldn't exist because the determinant would be 0. Okay, part B. State the value of k and find the value of a such that the following system of equations has an infinite number of solutions. Okay, so what you'll notice here is that the coefficients of x, y, and z here match the coefficients up here. So for infinite solutions, we must have then the determinant 0, and we know that k equals 3 gives that. So for 1 mark, k equals 3. And then we need this system of equations to be consistent. So I'm going to call this equation 1, I'm going to call this equation 2, and I'm going to call that equation 3. And I'm going to calculate equation 2 plus 4 times equation 1, because that'll get rid of my y's. Okay, equation 2 plus 4 times equation 1 will get to my y's. So that's going to give me 9x, 4y minus 4y at 0, and I'm going to get 6z plus 12z is 18z. Okay, don't forget k is 3. And then I've got 14 plus 4a. I'll come back to that in a minute. I need these equations. Okay, right. I'm going to do the same thing again, but I'm going to eliminate y from 1 and 3. So I'm going to do equation 3 plus 2 times equation 1. So it's going to give me 5x. 2y minus 2y at 0. 4z plus 6z is 10z. And I've got 10 plus 2a. Okay, so that leaves me with this system of equations, which we can see the gradient of these two are the same, which would have to be for infinite solutions. Otherwise, there'd be a unique solution. Now, there might be no solutions. It depends on the value of a at this stage. We want there to be consistency with these equations, i.e. we want these two lines to be the same. So if I times the top equation by 5 and the bottom equation by 9, the left-hand sides will both be 45x plus 90z, and the right-hand sides therefore must also agree. So I'm going to times the top equation by 5, so it's 45x plus 90z. That's going to equal 70 plus 20a. And the bottom equation I'm going to times by 9 to give me 45x plus 90z. And that's going to equal 90 plus 18a. The left-hand sides of those two are the same, so for there to be any kind of solutions to this set of equations, these two sides must also be the same. So if I've added 2a and I've taken away 20, that means that a must be 10. That's the answer. And finally, for 1 mark, interpret the system of a planes geometrically for the values of k and a found in part B. There's no coefficients here which are multiples of any other coefficients. That means that none of the normals are the same direction, or if you like, none of these planes are parallel. So the only way that they're going to have solutions with a determinant of 0 and being non-parallel is if these planes form a sheaf. And finally, on to question number 9. Use the standard results for summations to prove that for all integers n, positive integers n, the sum of 5r minus 2 all squared is equal to a sixth n, an squared plus bn plus c, where a, b and c are integers to be found. Okay, so we're going to split this out. It's going to be the sum of 25r squared minus 20 times the sum of r plus 4 times the sum of 1. So it's going to be the 25 out there. Don't have to. So I'll multiply out this bracket and split it out into the 3 sums. And now we can use the formulas. This one's in the formula book, and these two you need to know. So that's 25 times a sixth n, n plus 1, 2n plus 1. Okay, that's in the formula book. That's the sum of r squared. This one you need to know is a half n times n plus 1. We actually used it earlier as well. And then this one here, we're summing the number 1 n times, so it is n. Okay, common mistake here is to put 1 there, but it's not, it's n. All right, so I want to pull out something that's common to everything. So in terms of fractions, I want a sixth, and then algebraically I want an n, which actually fits with what's up here, so that's good. So I'm going to pull out a sixth n. That's going to leave me with the 25, an n plus 1, and a 2n plus 1 from the first bracket, first term. The second one, I pulled a sixth out, but there's only a half, so therefore I need a 3 in there. So that's going to be minus 60 times n plus 1. Okay, the n has come out. And then I need a plus 24. Again, to compensate for the sixth that's come out, and the n's come out, so that's gone. This is to tidy this up. Okay, it should come down to some quadratic, which assume doesn't factorise because it's left as a quadratic up here. So we'll have a 6n into 50n squared plus 50n plus 25n plus 25 minus 60n minus 60 plus 24 50n squared. 50n plus 25n is 75n, then minus 60n is 15n, and then 25 minus 60 is minus 35, plus 24 is minus 11. That indeed doesn't factorise, so that's the answer. You could state explicitly that A is 50, B is 15, and C is minus 11, but you don't have to because it just asks you to leave it in that form. So leaving it like that is fine. Hence determine the value of k for which this is true. So we'll notice that this is the same sum, just with a k instead of an n. So therefore I'm going to replace n with k. So it's a 6k times 50k squared plus 15k minus 11. So that's the left hand side. And we want that to equal 94k squared. Now we know k doesn't equal 0. Because k has to be a positive integer based on the definition of the sum. So actually I can divide that by k. I'm also going to times it by 6. So I get 50k squared plus 15k minus 11 equals 94 times 6. Which is 564. I have divided by k as well. So I could say I've times by 6 on k, and I know that k doesn't equal 0 for the reasons I mentioned earlier. So if I subtract that across, I'm going to get 50k squared minus 549k minus 11 equals 0. If I factorise that, I'll get 50k plus 1, k minus 11. Equals 0. So this quadratic tells me that k is either minus 1 over 50 or k is 11. But again, we know that k must be a positive integer. Therefore, k equals 11. All right. And actually on this one, it's a nice quick check, especially if you've got a calculator that can do summations. We want to do 5x minus 2 all squared between x is 1 and 11, and that comes out as 11,374. And if I do 94 times 11 squared, I get the same number. So you can use that as a check. Right. The fx991ex's will also do summations, so you don't have to have the graphical to do that. But that's a nice check to confirm that your answer is indeed correct. Because it says hence, you have to use this result. Okay, if you just did trial and error, you could get some credit, but you wouldn't get full credit because you've not used the previous result. Okay, command word hence requires you to use what's gone before. I think that's it. There's only 9 questions on this one. Yep. So that was the core pure paper, and there's one more video to come, which is on decision. So I'll go through that next, so stay tuned for that one. If you have any questions, even after I've gone through it, please come and find me. I'm happy to talk through anything that you're unsure about still, but hopefully this has answered most of your questions, if not all. Thank you.